So I'm curious, who has a class after this today? So most of you, I'm your last class, or at least a fair chunk of you. So you guys are almost ready for the weekend, right? It's always good to know if you're the last one standing in the way of enjoying your life. I'm sorry. So it's come up. Monday's a holiday. Hope you realize that by now. You shouldn't have any classes, but definitely don't come to this one. I won't be here. So we will meet next Wednesday. It'll seem like forever, I know. However, especially since it's the first assignment, you have 2 homework assignments before I see you again. I don't have another chance to remind you. They've been open since class started, so hopefully you've at least checked them out. They're due. The due date's posted on WebAssign always, so make sure you know when the due dates are. It's also in the schedule, that PDF calendar that you can have, so you don't miss these. This time they are both due Sunday night, right before midnight, so you have through the weekend. I figure most time when they're doing the weekends, I'm not seeing you, so you might as well have the whole weekend. There's no sense making it due like tonight, because if you want 2 more days, so be it. We're not doing anything for 2 more days. But so you have those. May I encourage you more than normal to start now, or at least try, be close, because it's your first time and there could be quirks and things you weren't expecting. Thus, I don't want you to get to Sunday night and something happens, or something you didn't account for, and you're going to be late, miss 2 assignments just because you procrastinated this time. At least be a little more proactive this time, if I can't encourage you to do it the rest of the semester. You with me? You're all aware? You've all seen the assignments? Have you all started them?
Just the quiz and the homework, right?
That homework 1's on the syllabus and logistics, and then homework 2's on chapter 1 and 2 about science and Newton's first law of motion, inertia. Now, granted, we haven't discussed all the info yet that's on your second homework assignment. That's what we're going to finish today. But it's always in your book, and there's you could have the large majority of it finished by now, except for the few things we haven't covered. So I encourage you to do that the rest of the semester. Open it up as soon as you can, get a feel for the questions. Then as you're reading the text and we go over it, Yeah.
Say what's our TA's name again?
The TA's name I did post on WebAssign, so when you forget, it's there. Jing Ma. Jing Ma.
Okay.
She has not yet decided her office hours, but she said she would and let me know. And while we're on that, it's on the WebAssign on the upper right under announcements. There's this another announcement about the lecture video, and that's where the web address is where you could go, where I post them on YouTube to review, or if you can't make it or something. Any other questions about logistics or what we've covered thus far? Or something cool you just see out in nature? If you ever have those type of things, I hope you feel free to ask in this class. They're very appropriate. So, like I said, physics helps me appreciate the world around us. I sure hope at least that as you leave this class, in between classes, you'll see things and recognize things and go, oh, I bet that's physics, or oh yeah, we discussed that, or I wonder how that one works. Bring them up, or discuss it in the class forum or something. Yeah.
Okay, so you offered for us to ask questions, so this is your fault.
Yeah, I'm one of those, if I don't know the answer, I'll tell you.
Because my sisters and I were watching Cloudy with a Chance of Meatballs. It's a movie about raining food.
Yeah, I like it. I like number 2 better.
They asked why the cheeseburgers fall together instead of falling apart as they're falling from the sky. And I was wondering if you could go over that.
Cloudy with a Chance of Meatballs, and the hamburgers seem to stay together as they fall, right?
The meat has more mass than the bun, and they were all
Okay. I feel I'm fairly confident I have a good explanation for that, and I think I can even relate it to what we've covered. So maybe we can make a connection here. Who can remember the definition of inertia? Oh, you guys are you're gonna have to know. Somebody goes, "What inertia?" Yeah, I've heard of that. What is that? What is inertia? Property of an object to resist changes in motion. Change in motion. That means changes velocity. Accelerate. Very good. See, notes come in handy. Thank you. So, in order to change something's motion, you have to apply a force. When you look up Newton's first law, technically it should be things at rest want to stay at rest, and things in motion want to stay in motion, unless a force is acted upon them to change its motion. So they're going to keep going the way they're going, whether they just sit there or they're moving at a certain speed. They'll just keep doing that forever until or unless some force acts upon them to try to change that. Hence, objects fall. We're going to study this more. They fall at a certain rate. You guys know this, gravity, the acceleration due to gravity. It pulls on them to make them accelerate at the same rate. It changes their motion the same. So the bun and the lettuce and the tomato are all being accelerated, trying to change their motion the same way. So when one speeds up, the other one speeds up just as much. And so they all move together. Yep. If there was a force between them, pushing apart, like a spring or some magnetic repulsion, then by falling, when you remove it, that force would dominate and they'd spring apart. First thing I thought of was something like this. Let's see. Let's just give an idea. This is good. You guys already have been asking a few questions before we get to them. That tells me you're thinking. It's going to be a good class. Here's two objects. Which one do you think will hit the ground first? This is heavier. Same time? You still think that? Because you've learned that, right? You're right. See? Your intuition is correct. Rely on it most of the time. Why? Is because they accelerate at the same rate. They went from zero velocity up to some velocity, and they did it together. So if they just, you happen to put the lettuce on top of the bun, it stayed with it until it hit. Then there was a force of the block coming back up that knocked it. Whee! And we'll get to study collisions in this class also. Does that help? Yeah. So as long as there's no force pushing them all apart, then they'll just fall together. I like that example. So we had this one, right? Guess I can be Bill. Did you guys think about it some more? So the handle of a hammer and the hammerhead. So if you're moving both of them together and you stop the handle, this has inertia of motion. The head, right? The red block. And so it wants to keep moving until a force changes its motion. What's the force that's going to make the red block stop moving? Friction. Yeah, it doesn't hit the table. The handle hits the table. The force is on the handle. It stops it. But this guy's inertia keeps going until friction slows it down. Somebody, it's like, I feel like it's kind of like a game show or something. Somebody called in and suggested, because they watched the video too and emailed me, not in the class, that when you're trying to seat the head on an axe, it's the same as with a hammer, it suggests they take a hammer and whack the bottom. Because that's the same, I'm moving this and stopping it, moving this and stopping it. So the same effect. Can you see the head's moving up? That would tighten it. So when I did it this way, the head moves up. And that's where I left it. So I'm exerting a force on the handle. And which way does the handle try to go? Down, right. Well, the red block isn't moving initially. Its inertia, state of motion now is at rest. Things at rest want to stay at rest. I tried to move the handle down. It did. You can see my hand recoil a little, right? I can't do it perfect. Well, if this is trying to stay put, and the handle moves down, it slides up until friction stops it again. So I think it's cool. You can move the handle either direction you want. Fun. Okay, so emphasize those two states again. There's inertia when the state of motion's at rest. Things at rest want to stay at rest. So you're in your fancy car, and this is you sitting in the seat, right? You're at rest. Something tries to accelerate you. Boom! The car goes forward. And what do you notice? Yeah, you feel like something's throwing you back in your seat. There's really no force there. It's just your inertia. You're at rest. You want to stay at rest. Something's trying to move the car, right? You're in the car, kind of like the red blocks on the handle when the handle's trying to move. So you resist that based on your inertia. Property of matter to resist the change in motion. Something's trying to change your motion, and you don't like it. Motion sickness. In a sense, it's often attributed to the fluids in your ear in combination with your other senses, and they don't make sense. You know, like if they're swooshing around or you're perceiving something move one way while you're not doing the other, some people, it doesn't mesh up as well. But you can think of these fluids are in your inner ear. They're like on a 3-axis accelerometer. You guys heard of that? It's like it can detect motion this way, and this way. That's how your phones know when you're moving them. Who's got the video games and they actually have a really small 3-axis accelerometer in there. Accelerometer, acceleration, change of motion. It can detect that and can tell how much you're moving it one way or another. The fluids in your inner ear essentially kind of do that. And if that's conflicting with other senses, it can make a lot of people sick. If you're spinning around a lot, right, and you stop, do your fluids stop like that? Because of inertia. Things in motion want to stay in motion. It'll take a while. Another one, you get hit with a boxing glove, right? Or you're in a collision and you hit your head. You can stop your skull from moving. It's like the handle stops moving. But what's inside your head that still is in motion? Your brain. Until it smacks into the inside of your skull to stop it. And it's that force there that causes damage. So here's things at rest want to stay at rest. Let's get moving now, right? You're moving along with it. You know, they try to stay together. I can't do it perfectly, but you get the idea? But then, you know, you're tooling down at 85 miles an hour and you run into something. So the car will stop, but not you. Which is why you all wear your... And that's exactly why. The seatbelt will keep you in place because something has to stop you. Do you want it to be the seatbelt or do you want it to be the back of a seat, the dashboard, or the windshield? Because it will stop you. Well, unless you go through it. But it'll hurt a lot more. Because you have inertia. You're moving and you want to keep moving. Do you have a comment?
I have a question.
Yeah.
I saw a video of a demonstration similar to what you're showing us, but this guy was in a car and he had a balloon. I think it was full of, I don't remember.
Probably helium. Was it floating?
It wasn't helium.
Oh.
He had a balloon that was filled with something else, because he demonstrated the helium first, and as the man accelerated the car, the balloon went back to the back of the car.
Okay.
Just like you're showing us, but he had a balloon for the second demonstration with, I don't know, I don't remember for sure, I think it was hydrogen, and the balloon as he accelerated went forward with him.
Okay. I'm aware of this. I don't know the specifics. And that seems counter, right?
Yeah.
Let me explain that then. We're going to cover that with fluids more, but this is good. So you're in a car. It's fun. If you take a balloon, if something that's more dense than the surrounding fluid, when we talk about density and buoyancy, but you could hang a mass, a cork, or a balloon full of air, and it has inertia because of its mass, and that would do what you're thinking because it's at rest, like this. So when the car accelerates, its inertia wants to stay put. So from your reference frame, it looks like it goes backwards. You can see it swing back. The funky thing is if you have a lighter than air balloon, something full of hydrogen, which isn't very safe, helium would work. It's floating in the surrounding fluid. Air is like a fluid, anything that can flow. Liquids and gases are fluids. What happens is the air is more dense and has more inertia, roughly, briefly here. And so when the car moves forward and accelerates one way, the air gets pushed back. It kind of shows back. It's actually more dense in the back of the car than the front. And that change in the density causes the balloon to rise and sink. We're going to learn that things that are less dense float, rise up, and things that are more dense sink. And if you're changing the density of the fluid around it, then the thing will move accordingly. So it's more to do with the, in terms of what we're studying now, the mass and inertia of the gases involved. And the ones with more inertia will resist it more and move back. And if they move back, they push the lighter stuff forward for the gas. Does that help for now? It's cool though. Next time you have a birthday party, grab a helium balloon. Take it in your car so it's just kind of hanging there. And it'll seem to go the opposite direction you're thinking. And then you'll remember back this class and go, oh, what the heck did he say? The air in the car is being shifted around that lighter helium balloon, in essence. Good questions. So you're going to have those two states of motion. I have a few things on my bucket list. One of them would be to go out into space and just chuck something. I want to just throw it. Because what would happen? If I got out away from things, I'm out in space, and I threw a ball. What's the ball going to do? We got to float, and we got what? Keep going forever, and you got, what's that? Heard something over there. Accelerate? See, these are all good guesses. That's why I want to do it. No, I know what'll happen. Okay, I exert a force to change its motion, right? To go from zero velocity to some velocity. Once it leaves my hand, is any force acting on it? No. If you're away from things, the forces are all going to be weak enough that you can't get rid of a gravitational attraction, but if you're far enough away from things, it's insignificant. So what do things do if they don't feel a force? They don't change their motion. So if this is going off at 2 meters per second, it'll continue in a straight line at 2 meters per second forever, until or unless some force acts on it. Sorry, I don't know if you can hear it, but I have a friend, a little infant. I can hear him pounding on the door. It's cute. Yes?
So if another force acts on it, will it change its speed or will it stay the same as it change direction?
When a force say that again, pretty please.
Are you talking about like in space though, right?
Yeah.
So another force is going to hit it or going to hit against it. Is it just going to change direction or will it change its velocity?
See, you guys are thinking more than my other classes. If a force acts on something, will it change its speed or direction is what you want to know? Or nothing. And I'm going to go ahead and cover that now, because it's the very beginning of the next chapter. In the normal world, non-science folk, these are about the same thing. Speed, velocity, they're synonyms. In physics, they're technically slightly different. So let me differentiate, and that'll help explain something, because we're going to need to know it anyway. Speed is how fast you're going. So it's like 85. Now that doesn't help you much. 85 what? Let's say miles per hour. That is a magnitude. It's also called, you might hear later, something called a scalar. It's how, this is a value. It's quantitative. How much? 85. That's the magnitude of this velocity. And it's a scalar, meaning it's just magnitude. That'll make more sense in a second. Velocity, oh, go ahead. Magnitude is generic for a value. If something is 2 feet long, then that's the magnitude of its length. If it's going 85 miles an hour, that's the magnitude of its speed. If I weigh about 180 pounds, I know, I'll admit it. That's the magnitude of my weight. What you can add to that is 85 miles an hour north. So that's magnitude and direction. That's called a vector in math or science, scalars and vectors. So the difference is it's important if something has a direction. I can say, you're going 85 miles an hour. I know how fast you're going, but I have no idea in which direction. So if you add the direction, it becomes a vector. Think of it this way. Here's 85 miles an hour. If this was like 10 miles an hour, then you can kind of represent it. 85 miles an hour, that way. That idea, scalar versus vector, magnitude and direction. And that's the difference between speed and velocity. So we use them interchangeably, but technically velocity is a vector. Direction's included. You need to know that. So back to your question. If you apply a force to something, we learned last time from Newton's second law, which we technically haven't even gotten to yet, that acceleration is proportional to force and mass. You push on it harder, there'll be a greater change. So that force will cause a change. It'll cause it to accelerate, which means change its velocity, change its motion, change its velocity. There are different ways to change something's velocity. You can speed up. That would change the magnitude, wouldn't it? You can slow down. That would change it. Positive acceleration or negative acceleration. By the way, acceleration is a vector. It depends on whether you're pushing it, it's trying to accelerate that way or that way. Speed up or slow down. So acceleration is a vector also. Since velocity is a vector, there's one other way you can change velocity. You can change its magnitude or its direction. So if you stayed going 85 miles an hour, but in a turn, if you're turning, you're technically changing your velocity. You're not changing your speed. Do you see how you're not changing your speed if you maintain 85 miles an hour? But if you change your direction, you are changing your velocity. Are you with me? And if you're changing your velocity, that means you're accelerating. And the only way that could happen is if you're applying a force. Yep. Yeah, I know. It can kind of sound like... So there's two ways to change your velocity. Well, three. But you can change your magnitude, speed up or slow down. Or you can change the direction, because velocity is a vector. And by changing the direction, you are changing the velocity. And we've learned that the only way to change somebody's velocity is, that means it's accelerating. A force was applied to make that happen, to change its state of motion. Yeah?
So does that mean if something's moving in a circle, it would never have a constant velocity? It's always changing direction?
Very good. If something keeps going in a circle, its velocity is constantly changing, which tells you there must be an acceleration there and a force. Have you guys heard of centripetal force? That's that, going in a circle. Because something's keeping it in a circle. There's a force needed there. Either something's pushing in on it or pulling in on it, like a ball on a string. Or you in your car, right? You're going around. There's a good inertia example. You're in a car, and you all of a sudden turn, like this. Which way do you feel like you're being thrown? If you quickly turn right, yeah, you feel like something's throwing you to the left, right? There's no force in that case. What's going on? Can you describe that? The car's going forward, and all of a sudden you turn the wheel to make the car go to the right. Are you at least mulling it over in your head, or are you just sitting there waiting for my answer? Which way were you moving? Your velocity was straight. Your velocity is changing, yeah. But it doesn't until, it's like the car goes that way, and you keep going forward until the car, the seat belt, the door, something pushes you that way, right? It applies a force onto you to change your velocity because you're changing your direction. And it's accelerating you towards the inside of the curve. That's a centripetal force. A force causing an acceleration, centripetal acceleration. That's a change in velocity, and in that case it caused you to change your direction. But we were happy with Newton's first law tooling along straight until or unless something acts on you to change that state of motion. So back to my bucket list. Didn't think I was going to get back there, did you? Yeah, if I chuck it, whoosh, it'll keep going at a straight line at a constant speed and velocity forever until or unless something acts on it. And that'd be cool to watch. We usually don't observe that, which is why this didn't really come along until Newton. Because most of the time we see this. It stopped. It stopped. Well, inertia. Things in motion want to stay in motion. It stopped. What are you smoking? Well, I think you guys know what's happening, right? Why does it stop? Friction. It would be happy to keep going. Let's get rid of friction. Blows air. Yeah, get rid of friction and it will keep going straight at a constant speed until or unless something acts on it. Now, remember this. Something can be moving. Let's take your car again. You're going 85 miles down the highway, and you maintain 85 miles an hour. Are you applying a force to the car? Does that mean there's no force acting on the car? Because you're not changing your velocity. 85 miles an hour north. What do you think? Are there forces involved? Can you think of one? Air resistance, air drag, wind resistance, trying to slow you down, decelerate you, accelerate you backwards. Okay, why don't you move backwards? If a force is being applied to that mass, it should accelerate. Continuous force? So something is accelerating you forward also, correct? The car engine and the wheels and technically it's the ground pushing on the wheels to propel the whole car forward, but you get that energy from your engine. So there's two forces involved. So here's your car. Oh, wee. Okay, and you're tooling down the road. All right. It's going to be very beneficial for you in this class to draw pictures. I like to call them pictures. They're technically called force body diagrams. That's just a technical term for pictures. Force body diagram. When you start getting multiple things going on, it can get confusing. And when you try to straighten it all out in your head until you've had practice, it can be confusing. So I strongly encourage you, when you're solving problems, to draw a little picture. It's very revealing. And sometimes people are like, I don't know how to set up this problem. I don't know where to start. I know where to start. Draw a picture so you know what's going on. Once you draw the picture, you can see a lot of things. For example, all right, I'm going to represent the mass as an object. There, a dot. There is, you guys said wind resistance acting on it. Which direction would that be? If the car is moving this way, it's some velocities that way. Which way is the wind resistance? Yeah, that way. Can you see now that force is also a vector? How hard you push, but the direction matters. So force, acceleration, and velocity are all vectors. So yeah, we'll represent the length as the magnitude. You know, it's some force about that strong in that direction. That's what force body diagrams do. So that's the force of wind resistance. And the other force, you've already told me, is the other way. Okay, I can draw it, but how long do I draw it? How do I represent the magnitude? Is it this length, shorter, or greater? Oh, gee, I've heard everything. Equal? Why equal? The net is 0? Let's go with that. Let's see. If we're wrong, we'll redo it. So if I draw it roughly the same length, does that look good? Good enough. Force of, we'll call engine. You know, getting you going. Are there any other forces acting on it? Gravity, which direction? Okay. Any others? Yeah, you are right. There is friction between the tires and the wheels. Instead of drawing another arrow, I'll just lump it into here. It's a force. All the force is trying to retard its motion. We'll just lump in there, but good. Anything else?
Would it be the surface of the ground or the road that push you up?
Push you up. And I heard somebody say normal force. Yes. And how should I represent that magnitude? Lengthwise, compared to the force down. Smaller? Force, I'll call it support force. That's how your book starts it out. As you go into physics, it's also called a normal force. So those of you that have heard that or not. Now, let's think about this and see if we got our magnitudes right. Yes?
If they were equal, though, wouldn't it be in equilibrium, so the car wouldn't be moving at all?
You're on to something very good. She said if they were equal, wouldn't they be in equilibrium? Yes. Then you said, so that means it's not moving at all. So you're thinking now these shouldn't be the same length? And that would, yeah, wouldn't have to be one be stronger than the other. So this is where you introduce the term equilibrium, and that's why I started all this. Equilibrium. What is that? The what? We'll go with that. The net force is 0. So you can think of it like this. You can also think of it as the sum. That's the Greek letter sigma. It usually means sum up all these, in case you're familiar with that. Sum up all the forces, and it'll be 0. Remember, force is a vector, so direction matters. So if one's going to the right, in this one, I think most people would say, going forward's the positive force. But if that's positive, to represent direction, we have to say this one's negative. Does that make sense? If these were the same magnitude and we added them together, what's the net force? 0. Okay. Now the net force is 0. That also should tell you now that if the net force, because technically this should be net, now that we're on there. If the net force is 0, what's the acceleration? Good. If the acceleration is 0, what's the velocity doing? Staying the same. Whatever it was. So if the car wasn't moving, it still wouldn't be moving. But if it's going 85 miles an hour, it would still be going 85 miles an hour in equilibrium. So equilibrium doesn't necessarily mean, and it's a common thing, does not mean something's not moving. It means it's not accelerating. There's no net force. It's not changing its motion. All those mean the same thing, you know now. So we can say that these are equal. If you're maintaining 85 miles an hour north, you're not changing your velocity. If you're not changing your velocity, you're not accelerating. There's no net acceleration. If there's no net acceleration, there's nothing causing it. There's no net force. There's forces acting on the car, right? We've just discussed that. But they're balanced. They're in equilibrium. Does that make sense? So given that, rethink this one. How should these two compare? Why should they be equal? Because the car is not moving up or down. The only way for the car to move up and down is if one of those were bigger than the other, right? So yes, I'm going to redraw that one so it looks about the same. Because it's not, coming off the road or sinking into the road. So horizontally, there's no net force. Vertically, there's no net force. This is in equilibrium. It's not changing its velocity, so it's happy keeping what it's doing. So I chose this example because you can relate to cars, and you're still moving. Forces are still acting. But you can still be in equilibrium with no acceleration because things are balanced. There's no net force. Is that clear? That'll help you finish your homework. Yeah.
So when we get farther into this and we're having to calculate this kind of stuff, would humidity play into that also or not?
Humidity. See, you guys are thinking. How do you think it would matter?
Well, I would assume that if there's a lot of humidity, it's got to affect this.
There's an effect. On here, would it affect one of these? Your gut's right again. So we're gonna discuss many forces in this semester. It's not just pushing or pulling. There can be electrical forces, magnetic forces. Fluids can exert forces over areas and whatever. And so what causes these forces or what affects them relies on lots of different things. Yeah, if you were, let's go extreme. Replace the air with glycerin, maple syrup. You're driving through maple syrup. Does that affect this force? Absolutely. And then that'll change what we just discussed. So you change the humidity of the air, the fluid it's trying to cut through, that would affect this force also. Just that way, if it was maple syrup, to maintain 85 miles an hour through maple syrup compared to air, would these have to be bigger or smaller? Bigger. Maple syrup's going to provide more resistance, right? So your engine's going to have to work harder to maintain 85 miles an hour. That makes sense, right? You're going to have to exert more energy and push harder in order to keep going that fast. If you didn't do anything and you're just happy tooling along at 85 miles an hour and boom, like that, all the air turned into maple syrup, you'd slow down, right? Because you're still doing this, but your resistance is now doing this. And can you see the net effect? F resistance, negative F resistance, let's add them together, plus the F of the engine is now not zero. This is bigger in magnitude than that. Bigger magnitude than that. So there will be a net force, there will be a net acceleration, there will be a change in motion and velocity. You slow down. So here's another example. you've read the text at all yet, our author of our textbook used to be a painter. And he learned a lot of physics from his mentor as a painter. So he likes a lot of those examples. So on the outside of a building, he's got a plank that they would move up and down to paint. So it's suspended there. And they would walk on it, obviously. Where's this one? All right, let's balance these forces. If he's not falling, they're happy right there painting. We can say they're in equilibrium. You're going to need to make some of these assumptions. Okay, it's just sitting there. Well, that tells me it's in equilibrium because it's not changing its motion. Boom! What do you automatically already know? It's not changing its motion, so what else do we know? The net force is 0. All the forces got to add up to 0. You also know there's no net acceleration, or we'd have a change in velocity. See, look at all these things you know already that you didn't think you knew. Just because this is in equilibrium. So let's look at these forces. I'm going to draw a free body diagram. Help me. What's some of the forces? Gravity acting on? Everything. Okay. So this one, he weighs something. The weight of number 1. The weight of number 2. I don't know their magnitude, so I'm guessing right now. But there's a force down on them. And the plank. Right? It weighs something. I put it in the middle, center of mass. You've probably at least heard the term center of mass. They call it where gravity would be acting if you could concentrate it on one spot. A nice symmetric, even board, it would act right in the middle. If this side were made out of steel and this side were made out of styrofoam, we'd shift it that way a little, right? Yeah, that's why I do it in the middle. Okay. Now those are 3 forces down. Does the thing move down? So what else do we got? What's holding it up? The ropes. Good. There's one here and one here. I don't know. Rope 2. Whoops. Rope 1. All right, if we sum up all those forces, let's say up is positive. You can say down's positive, but most people don't. As long as you're consistent in that problem. If you're going to say down's positive, just be consistent. I'm going to say up's positive. It doesn't matter. If up is positive, then we have a positive rope 1 going up plus rope 2 going up minus the weights, right? Because they're going the opposite direction. All of those have to equal 0 because it's in equilibrium. So if I gave you, what, 1, 2, 3, 4, 5. 4 of the 5 values, could you find the missing one? Good. Yeah. Did that. Here's a good one. A little more on that support force. Here's a scale. We'll see what I weigh today. It says hello to me. That's nice. Oh, well, good. I went down a little, at least from the last time I did it. So for a nice round number, it's 180 pounds. What direction is that, 180 pounds? Down. Am I moving down? So you see, you already know there must be an upward force of what magnitude? 180 pounds, because my net force is, and I am not changing my state of motion. Velocity is not changing. Right. What's providing the upward 180 pounds? The support force of this. It's pushing on me up, the normal force. Yeah. And all surfaces, when if you're in contact with them, they're pushing against you, supporting you. If you're at an angle, let's see, whatever that weighs. But if you're at an angle, it slides, right? There's still a downward force because of its weight. But this doesn't have to support all of that weight because it's at an angle, so it'll be a little less. And that depends on the angle and trigonometry. I won't make you figure that out in this course. But the support force is always perpendicular to the surface. So the support force, the force that's the scale is pushing back on this, is in that direction, perpendicular to the surface. That's actually why they call it the normal force. Normal means perpendicular at 90 degrees, if that helps you. But that support force is not equal to its weight in this case. They're not perfectly balanced. Now they are, it doesn't move. Now it isn't. See, it moves. The weight down is bigger than the normal force. So the net force isn't zero. I'm just trying to give you an example of that and explain that it's always perpendicular to the surface as we start tipping and doing things during the semester. Yeah? Yeah, your bones support your muscles and mass and everything, yes. And if you got microscopically to the surfaces where they're in contact, the support force would always be measured perpendicular to that surface. Okay. I had to, let's see, make sure I said everything. There were things I meant to say at the beginning. One, it's been brought to my attention that the modules unit in Canvas, the modules unit where you would do your clicker registration, seems to not be working in the Google Chrome browsers. I've addressed it with the company. I haven't heard back yet. Just try a different browser. Thank you for this first student that brought that to my attention. I said that. Is Laura here? Laura? Okay, good. Are you all cool? I meant to ask you last class, since you missed the first one. Oh, no. Well, if there's more, we can talk. But you guys good then till we see each other next Wednesday? Your 2 homework? Okay.